In this video, I'm going to look further at performing regression analysis in R, this time using time series data. The example I'm going to use is taken from a book by Thomas called Introductory Econometrics, the second edition, and it's the empirical exercise on page 336, where he estimates a Cobb-Douglas production function for the UK food, drink and tobacco industry grouping. The data set consists of 20 annual observations from 1960 through to 1979 on three variables: output, Q, labour employed, L, and the gross capital stock, K. So let's first of all load up this data set. It's in a CSV file, so I'm using the standard command here. So that's loaded my data set into a data frame. But of course, since this is a time series data, I now need to convert it into a time series object using the TS function as before. So here I'm specifying that the data is annual, frequency 1, it starts in 1960, and I'm using the data in FDT without the first column, because the first column contains a time variable which I don't need, as the TS function will create its own implicit one. We've seen how to do this in the time series video. So running that will give me my time series object, a matrix time series object, essentially a data frame, but it's also a matrix, which is the important bit. If we have a look at the data, as you can see here we have these three variables: Q, K and L, output, capital stock, labour, annual 1960 through to 79. So if you want to replicate these results for yourself, here's the data set that you need. I won't run the summary here. That will simply, of course, give me some summary statistics of these three variables as we've seen before. Let's just plot the variables. So using the plot command, which as we've seen before, if you apply that onto a time series object, you get a printout of each variable separately with the graphs stacked on top of each other. Obviously, if you want more complicated or more or graphs with better formatting, we've seen how to do that in the videos on graphics. Now, of course, in order to estimate a Cobb-Douglas production function, which is a non-linear function with linear regression, we need to estimate it in logs. So I'm going to create logs of these three variables with the log function here. So as you can see, I'm simply using log, then the name of the time series matrix. So it will take logs of all three variables, and then that's just put into a variable ln fdt. So if we look at that, you'll now see that this variable, this time series object, now contains these three variables in logs. I also need a time trend variable, so I'm going to create that here, again using the TS function. So I'm creating a time series object starting in 1960, which simply runs from 1 to 20, and it goes into this variable here. It's assigned to TTM. So if we look at that, you'll see it's done exactly what I wanted. So that's how you can quickly create a time trend variable. Now I need to add this time trend to my data set. So I'm using the cbind function, of course, to add an extra column to this matrix, lnfdt. Again, we've covered this in the videos on matrices. So that will have added this variable. Notice that, as I mentioned before, when you do this, it often changes the variable names to something that you perhaps didn't quite want. So I'm going to finally use the colNames function, again, where we've seen this before, to change these column names, these variable names, to something more appropriate. So I'm assigning this character vector here to the colNames. So I'm using lowercase letters here now to remind me that these are the logs rather than the actual variables, which were in capitals, and also the time variable. So doing that, and then finally, if I show it, you'll see I've now got my data set exactly as I want it. It's a time series object with the appropriate time values. It's in logs, and the lowercase letters indicate that, and I've got my time trend. So everything's ready now for analysis. Now in the example in Thomas, he first of all performs unit root tests on the three variables to test for the order of integration. He then proceeds to look to see if the variables are co-integrated, and finally estimates some error correction models. Now I'm not going to go through the whole of the same procedures that he does there, because we don't need that. I'm just going to illustrate how to use time series data in regressions. So the first thing I'm going to do is to run one of the simple ADF, augmented Dickey-Fuller equations, that Thomas runs on the labour variable. In fact, what I'm doing here, which is to run this test manually, you generally wouldn't do because in R, because R, as you might expect, has a package, an excellent package for carrying out unit root tests and tests of co-integration. And that package is called URCA, U-R-C-A. If we have a look at it here, there it is. This, as you can see, carries out unit root and co-integration tests, and that's the one that you would generally want to use if you're going to do this form of analysis. And I'll probably look at that in a later video. But here I'm going to do it manually, as Thomas does, just to illustrate the use of time series data. Now, as we've seen in the videos on regression analysis cross-section data, the standard R function for linear regression for linear models is LM. Now we're going to use that here as well. However, it turns out that LM on its own is not very good at handling time series data where you have lags and differences. It simply won't work with those. Fortunately, there's a very simple way around that, and that is to use a package called DYN. If you install this package and load it into memory, you can then use the LM function with time series data, including lags and differences, very easily. The only thing you have to remember is to prepend DYN $ at the start here. And if you do that, then the LM function will handle the data set fine. It will automatically adjust the sample period to take account of lags and differences. So everything works great. So this is a very, very useful package, and in fact essential if you're using time series data. So I'm going to load this into memory. Obviously you need to make sure you've installed it if you haven't done so. Now I can then simply use the LM function as normal, but making sure I put DYN $ at the front of it. So here I'm going to run this simple ADF equation on L. So of course I need the first difference of L as my dependent variable, and then my independent variables are the time trend, the first lag of L, and the second lag of the difference of L. So here, of course, as before, you specify the model. Now you can, of course, as I did in the cross-section video, put this model into a separate variable first and then simply include the variable. Here I'm actually just putting the whole model into the LM function. And then, of course, you specify the data frame where the data is. In this case, of course, it's the LNFDT time series object. So let me run this regression now, and everything works fine. Had you not used DYN and DYN $ here, you'd have got an error message. So we can now show the results using the summary command as before, and we get the familiar printout. And notice that the sample size has been adjusted accordingly to take account of the lags and the differences. Those variables are indicated here correctly. These results are perfectly fine. Now, of course, one of the requirements for running an ADF test correctly, so that you can correctly estimate whether it has a unit root, of course you look at the t-value on this lag variable here. It assumes, of course, that there is no autocorrelation in the error term, in the residuals. So we need to test for that. And of course, in general, with time series data, autocorrelation can be a problem. Heteroscedasticity not so much. That, of course, is more usually the case, usually a problem with cross-section data, and we looked at that, of course, in the videos on cross-section data. Autocorrelation tends to be the key problem here. So how do we check for that? Well, of course, first of all, you can use the informal method of looking at the residual plot. So here I'm going to plot the residuals. Notice I'm using that residuals function which returns the residuals from this model. So that plots the residuals. Of course, it's quite difficult just from residual plot to necessarily tell whether there's autocorrelation or not. They look reasonably random, but let's do something more formal. Another way, of course, is to plot the autocorrelation function, the correlogram of the residuals. Now, there is a built-in function in R for plotting autocorrelation functions, which is ACF. That's lowercase ACF. But in fact, a better function is the ACF with a capital A. Notice the difference. The built-in one has a small a small c, and a small f. This one has a capital A and then a small letter CF. And it's in the forecast package, which I've mentioned before is an excellent package. That is something you should definitely install. So I'm going to load forecast into memory, which then means I can use the ACF, capital ACF function in there on the residuals. And that gives me a nice autocorrelation function diagram. The advantage of using this is that it ignores the built-in one, shows the correlation at lag 0, which of course is 1, so it's not really necessary. The built-in one also doesn't seem to get the horizontal axis correctly labelled with the lags. So fortunately this one in forecast does it correctly. Now, as you can see, there seems to be no, these of course are the boundaries. So if the lines of course are outside of these two lines here, then the correlations are significantly different from 0. Here there appears to be no significant correlations, so it's looking as if the residuals are random or are non-autocorrelated. As well as the autocorrelogram, of course, you can run a lung box test, which tests, of course, whether a subset of the correlations are jointly equal to 0. Now you can do that with the box.test function, which is built in. And as you can see, you need to put, if you look at the little help pop-up here, you need to put the variable containing the residuals, or return the residuals, as I've done here. You can then specify how many lags to look at, how many, what number of autocorrelations to consider. You then also, if you want the Young box test rather than the box Pierce, you need to specify that here. So running the lung box test here, we get, let's have a look, then the hypothesis that they're jointly equal to 0 is not rejected. So this, again, that seems to confirm no autocorrelation. The other way of testing for autocorrelation, of course, is to use the Broich-Godfrey test, which is a Lagrange multiplier test, one of the standard tests used in the literature. As we saw with the Broich-Pagan heteroscedasticity test, this in the cross-section videos, this is contained in the package LM test. which, as we mentioned before, is an excellent package containing most of the diagnostic tests that you need. So loading that into memory, we can then run the BG test. As you can see, the function is simply BG test. So if I run that, if you run it with simply specifying the LM object here, fmod1, it will use it will test for first order autocorrelation by default. If you want second order or third order, you simply use this order option here, so this one will run second order. So I'm repeating here the two tests that Thomas does in his example. So first of all, testing for first order autocorrelation. Appears to be a possibility of that at the 5% level, although that's not what our ADF, our autocorrelation diagram seemed to show, and the lung box test. If we test for second order autocorrelation, that appears to be okay. In fact, these two values I get here are not the same as Thomas reports in his text. I've no idea why, because the other test that I run does agree with the results he reports, so I'm assuming that there's perhaps an error in the text, but anyway, it doesn't matter here, because I'm simply showing you how to use the BG test function to run the Roche-Godfrey test of serocorrelation. Okay, so that's how to use time series data here. Now, Thomas then moves on later on in the exercise, having run unit root tests on all three variables and tested for configuration, to estimate an error correction model. So let's look at how to estimate that. In fact, we'll do that in the next video.